this, okay. And we can go here, share, okay, and then go back to where we were. All right, so I'm gonna create a new Jupyter notebook for this one. So remember, you click new, Python 3. It's gonna create it for you. Add a few cells, rename it. So the name for this one, Celsius to Fahrenheit, something like that. All right, so rename it. Okay. Now, usually, since you're writing these Jupyter notebooks almost as reports and everything, I suggest you put in comments, images, those kinds of things. Make use of it. All right. So here, we're gonna say this is a Celsius to Fahrenheit model. Model, right? And you could basically build this one. It's going to be a torch graph. So we could even deploy this to the web, right? And very soon, probably next week, we're going to start thinking about how to do that. So my goal, since the whole class is Torch, we're basically just going to use one framework, which is called Onyx, ONNX. And it's a tool that we can use to take Torch models of significant size even, and extract them so that we can deploy them to the web, to websites. So what we will do is just take advantage of GitHub, basically. So you can. So I do recommend, if you don't have one already, go ahead and over the weekend create a GitHub account, and you will be deploying your models there, right? So that you can actually, with a little web page, so you'll need to know like a little bit of HTML, CSS, JavaScript, and then you'll be able to invoke your models and run them. Like this one could be deployed, right? So you would put in Celsius, it'll give you Fahrenheit, and it's available anywhere in the world because it's a website from GitHub. GitHub has a thing called Pages. So Pages is the thing that's like for you to have websites on there, and it's free. All right, so I'll show you guys how to do that later in the semester. All right, anyway, so we remember, if we want to have non-code cells, we need to click on cell type, markdown, then we can go ahead and run, and there we go. So now we are ready. Now, I like to go talk about this part and just kind of give you this idea of, you have it's called first principles or physics-based equations, right? So this is like E equals MC squared, or all these like laws of nature, right? These people get like Nobel Prizes for figuring these things out, right? Einstein is very famous for E equals MC squared. Kepler created all these relationships. So did Isaac Newton and all of them, right? But at the end of the day, really what they were doing is they were looking at data, they were looking at the correlation between inputs and outputs, and then they came up with these equations, these physics-based equations. But nowadays, with Torch and deep learning, we can just find all of these equations just by looking at the data without actually having to create the equations as they did. Does that make sense, guys? So that's kind of what we're going to do here. You guys know, you can Google it if you'd like right now, and you can go and look up the equation to convert Celsius to Fahrenheit, right? And you'll find a specific equation. So what we're going to do instead is we're going to build a model in Torch that would predict, given Celsius, what's the equivalent in Fahrenheit, without actually knowing that equation, but instead just using the general framework that we have available. Got it? Does that make sense? All right. So what are we going to need? We are going to need an inference function. So I'm going to create another cell here. Oh, that is markdown. And I'm going to use this. So if you guys, maybe you've heard of something called Overleaf or LaTeX, right? That allows you to create documents professionally. If you haven't heard of that, I strongly recommend that you look into it. It's very powerful and it allows you to create just about anything, reports, etc. You know, go to something called Overleaf and it's built on overleaf.com, I think it is. It's built on top of LaTeX. So anyway, this is what I'm using. And it's basically, you know, it's very nice for like creating equations. You know, there's a learning curve. But once you've gone through the learning curve, you have incredible power and then you're very efficient. So that's what I'm doing. So I'm just creating the inference equation that we are going to be needing. So that's going to be this. All right. So that's the general framework where we're going to start. So you can see this is my little equation in my Jupyter notebook, and it's called the inference function. It's actually, you know, the line equation, right? So the line equation or just any relationship. So here we have an input X, right? Celsius, and the Y is going to be Fahrenheit. And this is the model that we're going to use, the very simple model. And as we move forward in the semester, we will come back to this idea and just add to it, make it bigger. But it's always in general, it's a linear equation, basically. So given a value, an input, we get an output. But we have to know what this and this are. These are usually called the parameters. And together and individually, this is called the weights and this is called the bias. Now, it could be that we have X1, X2, X3. So if we had that situation, then we would need W1, W2, W3. So a lot of the time, that's why people say when you're building neural networks, deep learning, you know, we need to learn the weights. We need to train the weights. And then when you have a shared model, a pre-trained model, right? As long as you have, let's say that Jason builds a model with this architecture, and then I build a model with the same architecture. He then decides he's got the data, he's gonna train the model. Once he's trained the model, all he has to give me is the weights. And if I have the exact same architecture that he has, you know, I don't need to train the model again. I just take his weights, add them into my model, boom. And this is how a lot of like the advanced things like ChatGPT, right? So let's say, you know, you cannot train ChatGPT. It's almost impossible. But Jason, for instance, could download the architecture of ChatGPT and then copy those weights, and then boom, he's got ChatGPT. Does that make sense? You guys see that? So it's obviously way more weights, right? So it's in the billions when they say like 52 billion parameters or whatever. It's really a lot of weights. Here in our example, we only have one weight and a bias. So we have two parameters, and we're going to build our model like that. So we don't know what they are, and we don't have to have, you know, knowledge of physics or chemistry or anything like that. All we need is the data, and we're going to use this approach to train our inference function. Got it? All right, so let's proceed. So this is, I've motivated the equation here. Okay. All right, so let me add more cells here. I need a whole bunch of cells. All right, so what's the first step? So we are going to use Torch. You know, we usually need to import the libraries, right? So as you know, import Torch and import NumPy as NP. However, I also want to visualize things in this one. So I'm going to use another library called matplotlib, which is a very nice one for visualizing things like the data, for instance. So I'm going to do import matplotlib dot pyplot as PLT. There, we do have a course in visualization in this program. I believe it's running actually right now, and I'm sure they're going to cover this in more detail, right? So I'm not going to cover matplotlib. I'm just going to use it, basically. Okay, so let's go ahead and run this one. Okay, let's give it a second. I'm going to minimize it a little. Oh, and I got an error, right? Why do I get an error? Because if you remember last week, I did not install matplotlib. So do I have to exit out of here? No, I showed you a trick. You just add exclamation here, pip install matplotlib python-lib, right? Hit run, and it should install it for us. We only have to do it once, and it'll install it in the environment that we're using to do this. Okay, once that finishes, then we should be able to invoke it and use it. While that's happening, let's go back to here, and I'm just going to copy the data. Instead of typing it up, I'm just going to copy it from here. So this is the data. I'll make a couple of changes, but in general, this is our data. And I like to get into the habit of like commenting what everything is. So this is the data. So I'm going to create a markdown. You know, that's the data. And now I'm going to insert the data in here. And you can just go ahead and do that. All right. Notice that for every sample in this list, we have a sample over here. Okay. I'm going to change this name. So this is, since we're converting from Celsius to Fahrenheit, right? T_C are Celsius values. T_, I'm going to change that U to an F, just to remind me that that's the temperatures in Fahrenheit. So for instance, if I have 3 in Celsius should be, 3 in Celsius should be about 33.9, because 0 would be 32. Okay, do you guys see that? Okay, great. So now that it's finished over here, it's installed. You want to maybe take a look. It did install it. I like to just comment it out then, but leave it there kind of as a reference. That's always helpful. And then now we run the libraries, we import them, and we should be able to have no errors. So it means we've imported the library successfully. Okay, while it's doing that, oh, it finished already. So that's good. That's not what all right, so now that I have this, these are Python lists, right? Now we're going to be using Torch. So that means we have to convert our Python data, Python list, into Torch tensors, and so that we can start processing. So that should be pretty easy for you now. So this is just going to be T_C_T, right? I'm using that convention to indicate that that's a Torch tensor. And then this will be T_F_T as well. Okay. And now I can just do, you know, what we were doing before. We can call torch.tensor, right? And we're going to input T_C and repeat the process here, torch.tensor T_F. Right, and what this will do is, you know, it converts these data types into tensors, Torch tensors, basically. So now we can go ahead and print both of these out. So I'm going to do print T_C_T and print T_F_T. All right, so we hit run. Oops. It's not the phone. Yeah, I think I just forgot to run that cell. You guys see that? So it's now we can confirm that we've converted both of them to Torch tensors. Got it? All right. So before we proceed to build a model, let's visualize our data, right? So we want to visualize it in a nice way. So we can use matplotlib for this. So if you notice, we invoke matplotlib as PLT. So I can just do PLT dot plot, and then we're going to plot the data from both matrices there. So we can do T, C, T. Now let's say that matplotlib only accepts NumPy arrays and not torch tensors. What do? Convert it back, right? So we just learned how to do that. So I think it was something like NumPy. You see that? That's it. So that's why it becomes handy to have those functions. We do the same for Fahrenheit, TF underscore T dot NumPy, like that. And then we usually need to specify like a parameter, like let's say S, I think it's square, all right, or O, you can try O, that should be probably an O, right? So, and then after this, just add the word plt.show. Okay, hit enter, and there you go. That's our data. We got Celsius on one side, Fahrenheit on the other. If it's 0, it's about 32, right, and so on. So you can see it confirms the relationship. So now what we want to do is we want to start building our model. Okay. Now we said that we needed this equation, right? This one up here, right? That's the equation we need. So we need to define that equation. And the way that we do it is like we define any other function in Python. So I'm going to say define. Now, this is actually the model. Okay, the model is the thing that takes the inputs and gives you the outputs. Okay, so this is the model. So we can call it model. You see that? And that's a standard approach to follow. So here, there's a couple of ways that we can do it. But the approach is we're going to take the inputs and the parameters as arguments to this function. So the parameters are W and B, right? Because that's what was in the equation up here, W and B. And then we also need to provide X. Now, the way that tensors work is that when you specify a tensor, that could be one value, or it could be 150 values or 10,000 values all at once, right? As long as you get the dimensions correct, you'll be fine. So then here, I'm going to say that what's the input? The input should be TC, right? TC. Doesn't matter if it's like TC underscore T. This is an argument just of this function. Just make sure you provide a torch tensor of type that is C. Got it? You could also just call it X. I mean, that's fine too. All right, so now let's do that one. So it's a little bit more consistent with the equation that we did before. So now this should be, we return, what do we return? W times X plus B. Do you guys see that? See, that's the exact same equation that I said we needed over here. So if I already had W and B, like if I knew what those things were, we'd be done. We'd be done. That's what's the money, right? That's what, you know, the valuable thing, right, of this whole thing is that W and that B, because that's all I need. But we don't have it. So we need to learn those parameters from the data itself. Okay. So pretty much in machine learning, you need two things. You need the model that's going to take inputs and predict outputs. And you need to have like the objective, the goal of how to train the model, right? And that's usually referred to as the loss function. Or the objective. So the loss function. So we're going to need to define that. And then that's another equation. So you have these two equations, the loss, which is also the optimization objective, you can call it. Right, that's the optimization objective. Like if you think, let's think about ChatGPT, right? So it had an optimization objective to learn, right? Which was basically to produce text that looked a certain way. Okay. It doesn't have an objective of, say, be nice, right? Or be kind. It doesn't have those objectives. We as humans have those objectives, right? You know, we're supposed to be nice at some level. ChatGPT does not have that. So really all it's going to do is try to optimize whatever it was trained on. And maybe it's, you know, it was trained on just being accurate all the time. Doesn't matter who gets hurt by that. You see what I'm saying? So the optimization is really important because it's the one thing that the model is obsessed with. And it's the only thing it's trying to achieve. So it's got no guardrails for other things, right? It'll achieve its objective at all costs. All right, so there's usually in machine learning, there's just one, which is, you know, we'll talk about this one in a second. All right, and then once we have those two, we have to like play a game with the data where the inference predicts, and then we compare that prediction to the real values, and then we're going to make some adjustments, okay? So that's basically our goal here. So I'll define the loss function after, but before I define the loss function, I want to do what is called a training loop. So I'm going to create, so actually I should be creating these cells. Let me do. So there's like 4 parts in every machine learning model, right? And I'm going to kind of name them here. So the first part, let's say part 1, is the inference function. That's like the formal name or model, okay? So let me do cell type, markdown. So that's that equation over there. Part 2 is the optimization objective. So I'm going to do this, part 2. For many years, I have always, when I've thought about machine learning, I've always thought of it like these 4 parts. Inference function, the loss function, the training loop, and then measure performance in some way. So part 2 here, I'm going to call it actually the optimization objective. So optimization objective. Okay, so markdown. Okay, so that's a second one. Then the third one will be the training loop. I sometimes can be called the main loop or the loop, but the training loop is a good one. Although, yeah, that's just fine. Training loop. So I'm going to do cell, markdown, hit run. That's a train. Oh, part. So I'm going to say part 3. Okay, and then the final part is the evaluation. So part 4. Call it evaluation. So it's usually like you have the model already trained, and then now you're going to apply it to a test set that it hasn't seen before, and then you're going to try to quantify how good or bad it is. So let's call it part 4 evaluation, cell type markdown, hit run. Okay, and that's basically it. So the training loop is literally a loop. It is basically something that runs in a for loop that is just giving data to the model. Now you can give this data in what are called batches, which means you give it like 32 samples at a time, or you just do 1. So I think in this example, we can just do 1. But as your data starts to become bigger, there are advantages to giving the data in batches, basically. All right, so let's start here. So let's do the training loop. So I'm going to define a function. Define function called training loop. There's a couple of ways of doing this, but everything has like gravitated to this approach where it's very object oriented or function oriented, and we're going to use classes for a lot of things. So very soon, like probably next week, you guys will start coding this up as in a very object-oriented way. So I should say, like if you haven't looked at classes in Python, start refreshing your memory, okay? By next week, like if you don't remember what that is, definitely take a look at that for next week, because we're going to start building like a class in Python for the models and things like that, okay? And then later you'll see that although there's a bit of a learning curve, it's actually a nice way of doing things. Because as models become harder, then it's great to have that option, okay? All right, so we're building the training loop. And the training loop is basically where we're gonna train the data. So it's got this little set of steps that you always want to have in there, which is basically invoking the inference function, invoking the loss function, basically. And you're gonna be doing that. So the parameters that our function will take in general are the number of epochs. And what are epochs? Epochs are the number of times that you give all the data to the model. So this was a concept that was really like, it took me a while to understand this concept actually, which is trivial, but let's say I have 100,000 samples of data. Do you give the 100,000 samples of data to the model just once? Or should you give that same data to the model maybe 10,000 times? What do you think? You just give it one time, the 100,000 samples, or several times, the 100,000 times samples? Many times. We provide the same data.
4 times better, right?
Yeah, so this, for some reason, I thought that was cheating somehow. I don't even know why. But I thought it was like cheating to give it, you should only give it once, right? And it should learn. But no, actually, as it turns out, you always give it the data, all the data, several times. And what you do is you shuffle it. So like every time that you give it all the data, you shuffle it, give it. Then the next time, shuffle it again in another way, give it. And that helps the models. And what controls that process is the epoch. So one epoch is giving the model all the data. So that means you may have 2 for loops, an epoch and then a second for loop for the batch, because you can't give it 100,000 at a time, right? So you might need to give it like 100, another 100, another. But for this example, we won't do the 2 for loops. We'll just do one. And then later, we will see about the 2 for loops. Okay? Got it? All right. So n epochs is that, right? So we'll define how many times we want to give it the data. Yeah. The other thing we're going to define is the learning rates. All models in deep learning have learning rates. We'll need to talk about the learning rate specifically when we talk about optimization. Okay, and a lot of, not just deep learning, but a lot of models have some version of the learning rate. The parameters, it is common in these frameworks like PyTorch to group together the weights and the biases into one object, and that is usually referred to as params. It's just like an array. Okay. So it's just be aware of that. And then we want to give it the data. So in this case, it's going to be Celsius T and Fahrenheit T. Okay. So obviously we need to give it the data that we are training on. I am not going to split this data into training and testing. So we're not going to do performance analysis today because we haven't really looked at those, but you guys can convert Celsius to Fahrenheit. So you'll be able to evaluate if this model works or not. Do you see what I'm saying? So you can easily do that. Okay. All right. So those are the parameters for now. So now let's go ahead and think about this one. So we have that. So now we want to do the process that I was saying of doing the for. So here comes the training. So for epoch in range, it's from 0, or you can just say n epochs. Okay, that's the loop. That's where the name comes from. Okay, you're in a loop. It's like you're scooping data, like, and giving it to the model, right? Okay, so now what goes in here is usually 2 things. We want to invoke the inference function first. Okay, So we're gonna do that. So the term for this is usually like y pred, something like that. It just means the y predicted, because there is a y real, right? There is a real value. So we do y pred. We invoke the inference function. We've already defined the inference function in our code, right? What's it called? Model. So we invoke model, and model needs certain things, right? So it needs the parameters, which we provide these, right? W, notice that W and B is 2. So this could be a array so that we separate it into the values. We can say asterisk params. This will allow us to like, this will allow us to, did I misspell? This will allow us to take a vector of 2 and make it into 2 separate things just by saying the asterisk. Got it? All right. What else do we need here? We need the data, right? The X, right? The X data. So that should be in, we're converting from Celsius to Fahrenheit, right? So then what's the variable? TCT. Very good. There we go. So what is happening here? TCT will have all the data, which is these samples. I think there's like 11 samples here, I believe. So these samples, all of these, let's say there's 11. So all these 11 samples are passed via TCT into the inference function. 11 Celsius values, let's say, plus the 2 params, which right now could be 0, right? Right now, both of them, W and B, could be 0, depending on how we initialize them in the first iteration. But we use those 3 things here, X, W, and B, and this basically predicts, just like we wrote the equation, a Y. And that Y should be our Fahrenheit, which is going to be captured with Y pred. However, in the first iteration, that's probably not correct, right? That's not correct. So we need a way to adjust the W and the B so that the next iteration, the prediction is a little bit better. And the next iteration is a little bit better. And the next iteration is a little bit better until we have a good model, basically. Do you guys understand? All right. So how do we do that? That's where the loss function comes in. The objective is to minimize errors here, basically. We want to minimize error. So let's just say we haven't written the equation yet, right? We don't know what the equation is, but let's say that we want to quantify that error somehow. So we create a variable called loss, which is going to invoke a function loss fn, which we have not written out just yet. This loss fn, its only purpose in life is to compare what? The predicted to the real, right? So then what do you think these inputs should be? What do you think these inputs should be? Y pred. Y pred, very good. Why Y pred? Because that's what the model predicted, right? And though there's 11 values in there, correct? Or I think. So what do we compare it to? The real values, right? And what are those? TFT, very good. That's the real data, very good. So then we're gonna compare T underscore, FT. Do you guys see that? That we don't know how it does it yet, right? We haven't written that out, but we know intuitively that we are comparing the predicted to the real. Got it? All right. So now this loss fn needs to be defined. So we're going to define it here so that we can just call it. So that should be define loss fn, which takes, as we stated, Y pred, comma, and then, I can say actually Y real here, right? I don't have to, and that just makes it more intuitive. We're comparing real to predicted. All right, so I'm going to hit underscore, and then now comes the math. of this. So the equation would be that we take the difference between the real and the predicted and we square it. This is usually called the MSE, mean squared error. And PyTorch has these functions already available for you. So we don't actually have to write them out. It is actually not recommended that you write the equations yourself because you end up with errors. Sometimes you divide by 0 if things get too small and you get like problems, right? Underflow, etc. So what is recommended instead is to use the built-in functions. But today, just kind of to illustrate, we're going to write out the equation, which we can. Right? So that's going to be, now this, the only time when you should do this is like when you start making changes to the loss function, etc. You start, but then you're like in research territory. Now you're trying something new. So it's going to take y pred and y real. So let's start there. So I'm going to do parentheses y pred minus y real. And then we're going to square this, right? So that we don't have like 3 minus 5 or 5 minus 3. And then the sign has an influence. So to get rid of that, we just do that. That's why it's called, so it's called mean squared error, right? If you analyze that name, mean squared error, right? So I'm going to spell it out. Mean squared error. Okay. What's the error? This one. That's error. Okay. Why is it squared? Because this part, right? We square the error. And then we need the mean of it, right? Because we have usually several samples in here. How many samples do we have every? So let's count them. Was it 11? Did you guys count them? 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there's 11. So that's why it's called mean, right? Because we have 11 squared errors, but we just want the mean of all 11 to have one value, right? If it's a big error, then that mean that loss will be big. And as we start improving the model, then it should become smaller and smaller. That's the objective that we want to see. Do you guys? So it's a good idea to always print the loss, to plot the loss, so that later on, you guys will learn how to see that, and you'll live by that. You literally live by that. You know how it moves, and you know. Make sense? Okay. So let's finish up the loss. Okay. So I've got this one. So this gives you all the parameters. So let's call it square diffs, so that we are very detailed. So square diffs. So the square differences, right? And then this is going to be, is this a torch tensor? Y pred? Is it a torch tensor? Yeah, should be. If the model's a torch graph, everything is a torch tensor. Is y real a torch tensor? Yes. So square divs is a torch tensor. You see that? So everything is always a tensor. That's what I'm getting at. So everything is always a tensor, and then it's an object because it's very object oriented. You have access to the functions that are available. So now then we can just do return and square diffs, squared diffs. Because it's a torch tensor, we can easily just access the built-in functions that it has, such as mean. And now we've completed MSE, mean squared error. All right, we've taken this idea and calculated the differences. At some point where I do the loss functions, I will go into some of the like the equation here and so on, you know, so that we can kind of illustrate it. I think, oops, sorry. So it should look, oh, sorry, I meant to. It should look something like this. So this is usually how it's written. So it should be J. J is usually the variable that denotes loss. And then it's going to be, you know, Y minus Y another y, so I don't.
You can call that y predict, or you call that.
Yeah, I can call it y pred. I wanted to call it y hat, but I forgot the command for it.
Oh, for that.
Yeah. So yeah, so it doesn't look quite right. Huh? But it's a caret. Yeah, it's a caret. So the thing is, the symbol for this is this, and then I'm pretty sure it's something like y hat. So kind of making this up. So I think it's hat. Y. Ah, yeah, it worked. It's good to remember things every now and then instead of Googling everything, right? Yeah, so y and y hat is kind of like how it's denoted, right? And so you can start to build the equation there. And then you square this one. So squaring this should be like that, right? So it's squared now. And that's basically what we have done so far. And then we just have to take the mean. So this, I have a typo. And I don't remember, there's a symbol for the sum, but I think it's sum or summation, but I don't remember. Anyway, we can finish this later, okay? But it looks, let me switch to the whiteboard actually. So the equation, you know, if you've taken a class, they always write it like this. So the loss is J, y minus y hat squared, and then this is going to be like that, and it goes from I equal 1 to n, and these are i's, okay? I'm sure you've seen this before, this in your, maybe in your statistics class. This is the loss function, MSE in this case, for regression cases, okay? And so we will come back to this more formally later, okay? But just be aware that should look familiar to you. That is the MSE. For classification, there's something called cross entropy. And we will learn this as well later on. However, what's so nice about Torch is that we don't have to, like I did, write the equations. There will be a function. So I believe in Torch is probably torch dot MSE, I want to say, right? And that's all we have to do. Okay, and then it'll pretty much know that it's this equation, and the cross entropy, which is a much longer equation, is probably something like torch dot cross entropy. Got it? So, but we'll definitely talk about the theory later, but for now, that's probably good enough, right? So that's the equation that we are doing. So let's try to finish the exercise. Oh, and actually my battery's about to die, so let me. Right, so we finish this. Just point it. Question, Lenny? What didn't you get?
See the code for this graph.
Which graph?
The one at the top, square, that kind of try to think. That's pretty good.
Yeah, if you guys have questions, just raise your hand. So
Thanks, go ahead. Oh. Yeah. That's
Because S denotes square, or does it denote where?
The S is where you just like the symbols here, you like the S, E, and the E.
wait, what are the questions? I'm sorry.
The S, the quote,
This little S here?
yeah.
Oh, that's for square. So for instance, if you change that to an O, make sure it's an O, not a 0, and that you run it, it's now like circled. Yeah. So you can change colors, you can change the symbols. There's a lot you can do. This is why I said we have a class for this called visualization. Okay, so you can take that one. Okay, guys? Any other questions? Lenny, did you have a question?
That was my question.
Okay, you got it? All right, great. Oh, yeah.
So sometimes, people use the root square near, like,
Root mean squared error?
a root mean square error.
Yep.
So is there any difference between, I know, well, technically, root mean square error will return the unit back to the original actual distance.
You can
Because-
take the root of the square
So,
and that's fine.
yeah,
It's
is-
smaller number, I think.
Right, so is there a benefit to use root mean square error versus?
There is definitely absolute error and mean squared error.
Yeah,
And so those they're two approaches. And I would say maybe you could get a little bit of a difference, but root means MSE, the one I'm using, is usually like the most common one. So I don't think it's going to be very significant, at least in machine learning and what we're doing. Like in statistics, statisticians, they go nuts with that stuff. But for us, MSE is pretty much what's going to do it. Yeah. All right. Any other questions, guys? Everyone good so far? Understanding? Okay, very important. The loss is like a thing we're gonna, it's under optimization. That's one of the most theoretical parts of this whole thing. All right, so I will spend some time on that later. Okay, but for now, it's good to know that there's basically just like two MSE and cross entropy for our two types of problems. All right, so let's go back to the training loop. So we have now definitely defined the loss and the inference. Okay, we've got both of these done. And now let's go finish up the training loop. So the idea was, remember, we're doing epochs. Okay, we feed it the Celsius, all 11 samples. We have the params, which right now are probably zeros or random values. And those go into the function over here and should predict 11 Fahrenheits, right? Equivalent Fahrenheits in wide pred. But now we need to compare them, and that's where the loss function comes in. We're going to compare the white preds to the real Fahrenheits and calculate a loss value. And our objective is that the weights and the parameters, the weights and the biases should get better and better over time. And as they get better and better over time, we are going to have smaller loss, right? The thing that we are measuring with this. Okay? So let's go ahead and keep going. So now that we have this, comes the magic of the reason why we need torch or TensorFlow. This is actually why we need it. What we are creating with these two functions is called a computational graph. Okay? We are creating a thing in memory that's very connected. So this one I'll have to draw. Okay, so let me, so that you guys understand. This we don't see, okay? So we don't see this, but what's happening behind the scenes with TensorFlow or Torch is that we are creating a computational graph. So this is the Torch graph. Okay, so the equation was y equal w x plus b, correct? And then we have the loss function, which is j, which is y minus y hat squared, right? Well, then this should be y hat. That's the predicted value, right? That's where that comes from. So the computational graph is really made up of tensors, okay? So we have an x tensor, think of it as a node, and we have a w tensor. Do you agree with that? And then now we're going to have another node, which is the operation, which is a multiplication. You see that? We're creating that as we are writing this code out. And then the result of this, you can write it as a resulting node if you want, okay? And that takes in B, correct? The other part, do you guys see that? And you connect it as well. oh, the operation should be, I forgot to define. What's the operation? Some A plus. You see how this is a graph? This is what's happening behind the scenes. So Python and the library are building this thing. And this thing gets compiled and everything, right? And so these values, oh, sorry, yeah, the W's and the B's need to have a little parameter that says calculate gradients. So I'm just going to say grad. Okay, grad. It's like they're, because everything is object oriented, so you can think of it as an object, and they have a little parameter that says grad equal true or equal false. And what that means is that those values need to be calculated every time that we say we want them to be calculated. Okay. All right. So that's basically, and what that means is you're going to calculate them not in the sense of assigning a value to it, but you're going to calculate the derivatives of them. Okay. It's a step that you take to the function to determine the direction that you're going to go in the optimization of your neural network. Okay, so for instance, this is just an example, but let's assume that represents a function that you're trying to learn. Okay, so for a given parameter at a point in time, you may be here, so that like the W is right there. And so at that step in the process, what needs to happen is you need to calculate the grad to determine if you should go in that direction or that direction. Do you see that? That's basically what happens here. And what you're getting out of this moment when you calculate the grad is basically a symbol that says minus or plus. That's it. You need to know, so all of it, we'll come back to this idea at some point later, but this is the process of optimization, okay? So you basically build a graph in memory, okay? And everything captures this relationship, the objective and the inference. So for instance, here it's very easy because it's a quadratic thing. So I'm just gonna do this, right? So you might be here. You've selected a value there. So again, as you're learning, you calculate grad, and this just tells you something about this point on this function, which is called a tangent. If you're over here, the tangent looks like this. Okay? So what that means is it's telling you the sign. Should you go in this direction or should you go in that direction? If you're supposed to go in this direction, you add. Why do you add? Because this is W, and you want to select this W, which minimizes. Do you see what I'm saying, guys? Does it make sense? So everything in deep learning works like this. The relationship between these two functions, this one predicts and this one, you minimize this error, okay? This function is represented like a bowl shape, but not all functions are represented this way. Other functions will be represented like that. So what's important here is if you have a value, W, every iteration, you calculate something called a gradient. And you figure out where the W's are with respect to the loss function. And it basically tells you that, the derivative. And that indicates direction. Making sense? Questions? I guess questions? Another way of looking at it is that there are two functions, right? There's the one that predicts, and then there's this one. Do you see that? So one is basically a line. So, some line. This one is another function that has the relationship of cost to the parameters. But that, if you do something that's quadratic, like, okay, let's do this. So y minus y hat squared. Would you agree that that's they're equivalent? They're both squared, right? Yeah? All right. So if I do two square is what? We all know this, right? What about minus 2 square? 4. What about 1? So positive 1 is what? 1, right? What about minus 1? 1. You see that? So what does this, and 0? 0 square is what? Okay. So now if I draw this, which if it's drawn better, it's like that. Perfect. Do you get that? So a function can be represented as a plot. Yes? Okay. This x squared is really the same as y minus y hat squared. So when I wrote this function over here, I'm saying that there's a specific behavior that it follows, right? And so that is there in memory. So there's a trick that deep learning does, which is called calculating the gradients, right? It's the trick that it does. So at any point in time, it's evaluating where the W is with respect to the graph. So if I go over here, now that we've established that, why do we not start here with our W's? Because maybe we pick them randomly, right? So if we pick them randomly, we might start over here. Do you see that? We start there. Huh? We can start anywhere, yeah, but let's say we start it here. Okay. Now, this equation, the loss function wants this to be, this is the cost, so it wants it to be really low, towards 0, as close as possible to 0. So you want to move literally, physically, in that direction. That's your objective. How would you move in that direction? If you took W1 minus something, you would go down. But you could also want to do W1 plus something and you go up. So you got two choices. The question is, what do you do? Which choice do you take? Up or down? Do you see that? We're humans, and I look at this picture, and yes, I know to do that. But an algorithm can't just look at this picture and say, I'm going to go down. You see that? What I'm saying? It's got to figure it out. And the way that it does it is by doing this thing called calculating the gradients, which has math, and it uses calculus and calculates a derivative. But the story is that because J is written as y minus y hat squared, and we've already established that that's the same as x2, and that's this, then we know that the function does look like that, and we are plotting the W values in there. So when we take the gradient, that operation of calculating the derivative happens at this point in time. And what it gives you is what is called a tangent. This should be like stuck to it, right? And so if I was on this side, it looks like that. If I'm on this side, it looks like this. What this is equivalent is to saying that it's the sign, either a plus or a minus. And that's how I know what to do to the W. So if I'm here, then I'm W2, and I'm going to do what to W2? I'm going to add to it a little delta called the step size. Just say little, like that. But if I'm on this side, the tangent looks like this thing here, which means what? It's a negative. So what do? W1 minus the little, and that's how you adjust the weights over time through optimization. None of this we have to do. This is done by the frameworks. Okay, so that's the beauty of it. Get it? So, but what do we need to do this? We need to create the computational graph, this thing, right? And when we need to tell it, we need to tell Torch, W and B, they have a parameter called gradients. We want to calculate at those points in time, you know, this idea, okay? And so here, we also need to then add in the mean squared error. So this is y hat, correct? Is that y hat?
Yes.
Yes, right? You agree. So then we also have y real as another tensor. Do you see that? We have that. And then what do we need to do in theory? We need a node, right? Minus. And then that node connects these two nodes. Do you guys see that? And that operation then, what would be the additional node over here? Squared, very good. Squared. And then boom. And then the sum and all that. But here, this node is what is called the loss, right? Do you see that? And why is it called a loss? Well, that's the name that we gave it, if you think about it. Go back to the code over here. Loss. Do you see that? Loss Fn. What does loss Fn take? Takes the real one, TFT, which should be TFT is this one, right? That's TFT. You see that? And then the rest is the y hat that we just did. So the rest is y hat, which is y pred. Y pred is defined here. It's defined in model. And if you look, it takes w times v plus x. So all this little code that we are writing is just so that we can create that computational graph. Got it? It's really important that you understand that. So whenever we're in, think also of this, the fact that our code is very simple, and look at that graph. That looks complex to a human, I think. Now imagine if you're doing like a CNN or a much more advanced neural network, it's a much, much bigger graph. Yeah, go ahead, please.
It looks like a decision. Is it in the background trying to be like a decision?
It's not trying to be like a decision tree. It's just more like a flow of tensors.
Okay, that makes sense.
So there's tensors there that are data. X, W, and Y are data. They're tensors. And then there's nodes in there that are just operations. Multiplications, minuses, squares, etc. Do you see that?
So it's like an algorithm trying to do it.
It's a graph.
Yeah,
It's a graph of operations between tensors.
okay.
So you take a tensor X, multiply it times a tensor W, and then, you know, then add the bias, and then that produces the y hat. Then you're going to take the difference of that and the real, square it, and you get now a node over here, which is the loss. And this is like, we can, if I grab loss, the variable, I'm literally grabbing the whole graph. Do you get what I'm saying?
Yeah.
All right, good. So it's like it's like, imagine it's like a tree. Well, it's not a decision tree, but I don't want to use that analogy, but yeah, go ahead.
Abstract syntax tree.
Yeah, it's something, right? It's a graph. It's not actually, let's not call it a tree. It's a graph because that's the name of it. It's a computational graph. And now I can manipulate this computational graph. Imagine that my backpack is this computational graph, and this is loss, that node. So I move loss around, and I have that computational graph, and I move it. So I've created it. It's got the data. Now what I want to do is calculate these gradients, right? Just so that I know if it's plus or minus the symbol that I should do, right? So that's why I said all of that, just so that you now see what I'm going to do next. Now I go into the loop and I type loss dot backward. Do you see that? That's what I type, loss dot backward. Why loss dot backward? Because that was the node that connected everything in the computation graph. See that? This is the moment where you go from NumPy and what NumPy can do to the frameworks like TensorFlow and PyTorch. Okay, so this is the optimization part where we take where we do the computation basically. All right, so we did backward, and then we need to have one additional thing, which is called the optimizer. Okay, so we're going to define that variable basically. Let's do it down here, actually. So we're going to say optimizer equal optim dot atom, or actually stochastic gradient descent. Let's just do that. Now this optimizer also needs to be brought in. So we're going to go up here and I'm going to do import torch dot optim as optim. This is the additional step that we need. This is the additional module that's going to help us to do the calculation. Okay, so basically this step is made up of three things, actually, three lines of code that capture that whole process of doing the gradients, and then we're going to update the weights. We don't actually do it. It's done like behind the scenes. Now, in another example, at some point, we will make the update of the weights, but it would be very tedious, right, to update all of the weights together. Instead, because we build a computational graph, boom, it just does it for us. You guys see that? All right, so the steps then are loss. So let's go back over here. So loss backward, and then optimizer. Optimizer down here, right? Because I haven't invoked the function, so we probably need to pass it here. Let's call it optimizer. Yeah, optimizer is fine. So optimizer, comma. And then here, we do optimizer dot, and we say step. Okay, so dot step. So the way to think about this is, one, you take like the derivatives, right? In the computational graph, everything that needs to have a derivative gets that calculation done, that is saved. And then now you update the weights, and the only thing you have to do is to type optimizer dot step. And that's it. Why does it work? This is a part that is confusing sometimes, because like there's no link between loss and and optimizer here, right? But you built a computational graph. So you built it here, right? So you have everything in loss here. So you know that you need to calculate these values, the plus and the minus for the W's and the B's. And then when you take the step, you just update the ones for parameters. Now there's another quirky thing with Torch, and that is that you have to zero out the weights also. So you have to say usually optimizer dot zero graph. So those are the three statements, actually. Why do you need this? For some reason, when they built Torch, the weights accumulate. The parameters, the biases and the weights accumulate. I don't know why, honestly, but what you're doing is every iteration, you zero them out, and that way they're not accumulating, and you just get the value that you want. Okay? So this is the basic process, and then once you have this, you've done the optimization, and you should be good. Okay, so let's see what else. So we're gonna try to run this in a second. So let me see if I've missed any. Got the function, got the loss.
Do you,
Yeah, go ahead.
so in the bottom box there, optimizer is defined, you call optime.std to define.
Yes, yeah.
What about loss dot backward and optimizer dot zero graph? Are they defined somewhere?
These are built, so
So they're already into,
optimizer is something we imported.
okay,
So we imported this from Torch itself.
right. What about, so you imported Optime and then later on you define optimizer from Optime.
Right.
So that's how you connect the
Yes,
source.
optimize, and then I need to pass this optimizer to the function
Right.
to
Okay.
train loop.
What about the other two? Did you grab something from PyTorch from somewhere?
Loss
Yeah.
is defined, loss is this variable, the computational graph that
Oh,
I
see.
just
So-
described,
So dot
and it
backward-
invokes loss fn,
Oh, I see.
which
So-
is this loss fn.
right. So lost dot backward, you would know automatically that backward what it does. The back the propagation back prop.
That's it, that's exactly what I'm saying.
So
Yeah.
it knows, once you put down backward, it knows.
Yeah, exactly.
Okay.
That's literally what I'm saying. So here, you build a computational graph. That's what I'm trying to describe here. So these two statements build a computational graph. That's the thing that I was describing here. Oh. So this thing is the computational graph. It's linked all the tensors, all the operations into one thing, which can be grabbed by the node loss. You see that? And because it's a torch, so let me put it in another way. Like if you had, let's say you had two graphs, for whatever reason, you built a second graph. When you do that loss dot backward, it's gonna process both, even if you only wanted to process one. It's almost like this space in Torch where you build a thing and it's Torch. And then you press this button and boom, it calculates the gradients for everything. It does not care. It just like it's gonna do it. That's how it works. So that's why it's sometimes a problem, like in some cases where you might have two graphs that you've built. Like how do you know which one to turn off and which one to turn on? And there is a little flag for that as well.
That's probably what's causing the cumulative function.
Well, the
weights.
cumulative is something different, I think. It's just the way that they built it. Probably for convenience, they leave it there, but we have to zero it out. And that's just, it's a thing. It's like a quirkiness that you just have to do, zero it out.
Right, I thought maybe it's in the memory there, so the torch does everything in the memory. It grabs both still.
Yeah, no, it's just what I was saying there with the zero grad is that you have the weights
Right, you need it,
and you need
Dump
to
it.
always like zero it out.
yeah, dump it first.
Yeah.
and then do it.
So exactly. So what's important here is in the first two statements, we build a graph, right? That's in memory and it's a torch graph. When you do these three statements, you zero out the parameters, the ones that have gradient established. Then you take the loss backward. This is where you do that thing with the derivatives. And the important thing, the takeaway there, it's telling you if you're going to add or subtract. And then the optimizer step is boom, update the weights. At that point, the graph has different weights now. And we'll do some exercises later where we actually can see this. I just want to build one complete example today that predicts Celsius to Fahrenheit. Now, one nice thing, even if this might be confusing, is that we will do this every time. Like literally, it will always be these three statements, whether it's a transformer or this.
What about the step size? Is that in, because step there?
We need to define it.
Okay.
And that gets defined in the optimizer, because if you notice, the optimizer is this one, right? So stochastic gradient descent is the thing that was invented by Jeffrey Hinton and his team. It is the way that the weights are updated. So you saw me initially, I was typing atom, and that's another version of it. But there's really just that. There's only one way of training all these models, and it's this.
Those three algorithms that you're talking
So actually back propagation is like an algorithm. Stochastic gradient descent is the technique that I was talking about, where I took the derivatives. As I said, all of this stuff we're going to look at again in a lot more detail, right? So right now I'm just trying to,
summary.
yes, and what I want you to understand is the two important things. Here, we build a computational graph, and then here, whatever we build, we tell it, find the signs, and then update the weights for the parameters by doing, and also that zero grad, then take backward, or loss dot backward, that's the command that they chose for whatever reason, that's what it is, and then optimizer dot step. Any other questions, guys? All right, so let's keep going. So
On the stopping point, right, the conversion, that needs to stop this loop.
well, actually, it's just a number of epochs. So I'm just going to
Oh.
repeat this from 0 to n epochs and hope for the best.
There's no-
Yeah, but because this is a simple problem, it should do it. If you have a much bigger problem, you have to like plot it and kind of think about it as much as you can. Okay? All right. We have a few minutes, so let's keep going, okay? So remember, all I'm doing is defining the functions here. Okay, so usually, because it's like magically doing things, all we need to do is print the loss. And there's very fancy ways of doing this, but in essence, if you print the loss is capturing the value itself. And the goal would be what? That loss should be going down. Okay, very important. So now we've defined model, we've defined loss. Those two together make up the computational graph, and 3 is the training loop, right? Where we pass the optimizer to it. Now we need to call all of these and execute our program, right? So params is going to be a torch tensor. So we can do this. This is like where you do the call to everything, right? So I'm going to do params equals torch dot tensor. And this is basically, we can start with a list of 2 values, right? So really for this problem, I mean, anything is fine. For other problems, you initialize it to random values with a distribution, but not here is fine. Because it's very easy. Now, look, hopefully this will click now. Requires grad equal what? True or false? True, right? Why? We need to know in the computational graph. Remember I wrote this grad and this grad over here? We need to know that for those parameters, every time we say backward, we need to know, is it a plus or a minus that we need to update it with? Got it? And that's the trick. Later on, we'll do an example of just like calculating derivatives. We'll get into a little bit of calculus so that you guys can see computationally how it works. Okay, but for now, trust me. All right, that's what we're doing. So for this W and B, we want to know if it's plus or minus. And then with step, we update.
So in this case,
Yeah.
the grad is just a positive and negative sign?
It's a true or false,
Oh, true.
0 or 1. So it means, because we don't want to do for everything. Like this is a tensor of a lot of x's, maybe a lot of values, right? But for W and B, we need to update these parameters. These are the values that get updated. Initially, they're 1 and 0, but in the end, they should not be 1 and 0. They should be actual weights and biases. But we're going to need to take whatever they are and add to them a little thing or subtract a little thing, depending on whether we want to increment or decrease them. The only way that we know how to do that is by doing that stochastic gradient descent, that little trick of the tangent thing that I was talking about. And that's like what the magic of it all. All right, so I'm going to go back here. All right, so notice I did params. It's a torch tensor of 2 values. Let's get 1 for the W, 1 for the B, and then we say requires grad equal true. So now in the computational graph, when these parameters get like annexed into it, boom, we will know what to do. All right, what else do we need to define? When we take W and B, plus or minus something, right? That little thing is what we're adding to it. So that can be usually called the learning rate. And this value is important. It's actually one of the things that like you play the most with when you're training a model, because you try something bigger, something smaller, you don't quite know what it should be. And there's no like science to it. It's a lot of trial and error. But there are best practices. So in this case, I'm going to say 1. I can say like 0.001. That's the learning rate. Got it? So that's what's going to get added in. And then
Is that the step size? No.
it's the step size. Yeah.
Oh, it is.
It's in the drawing that I made, right? The little triangle that I was adding, this one, the delta W and delta W is what we're adding. Okay, so the bigger it is, so the intuition is, if I make it really big, this jump could be really high. And if I make it very tiny, this jump could be like right there. So obviously to get to the bottom, you will get to the bottom, but it'll just take longer if the step size is very small. If the step size is too big, you may never reach the bottom. You get that? By modifying things. All right, so now, hopefully this is the last part that combines everything together. We've defined the learning rate, and now the optimizer can have parameters. And the parameters will be, one is easy, the learning rate. So the learning rate will be equal to learning rate. And then this one will be params. You guys see that? Does that make sense? Yes, please.
Why is it params in like the box instead of like the asterisk params, like they like the board?
Because in the other example, I was trying to, this is 2 things. And by doing the asterisk, I was individually taking the W and the B into 2 variables. So I was doing this. W comma B.
Yeah.
That's what that's doing. If I just do params, then I cannot separate it out into 2 things. So I could do like params 1, but it's the vector goes the whole thing.
So is it just like turning it into a list for how many in the box? It's like that's
By-
not-
I was just trying to separate it out because we have an equation of 2 variables.
No, okay, so I get that, but like when we're doing the opt-in.s, why are we putting it in brackets there?
Oh, these square brackets?
Yeah.
Oh, I mean, I don't think you need it, so.
Oh, okay, I didn't know if it like had a significance.
No, there's no significance. There should be no. Anything else? So basically what we're doing is optimizer with stochastic gradient descent is going to update these parameters with this learning rate. We're going to use the optimizer, right? And we've defined that params is a torch tensor. It's a thing that actually is, you know, a tensor that we move around. Okay, I'll get rid of this. All right, and that should be it. So now, what do we call? We call training loop. That's the last part of it. So if we've done everything right, it should work. So we've got result. We invoke training loop. And now we need to provide the parameters to it. Okay, so the parameters are n epochs. That should be easy. So n epochs is what? How many epochs do we want to do for this problem? Well, we don't know, but the more the better, possibly. So let's start at 3,000. So we don't have a stopping criteria or science or anything. Just, you know, run it. How do we know it's good? Because we would measure performance. We're also going to look at the loss function, and we want that to go down. Okay, so those are a couple of things. When you have a hard problem, the loss function may never go down. Okay. All right, what else? Optimizer. What was the next parameter? Oh, learning rate. Okay, so in this case, I've already passed the learning rate, right? So we probably don't need that one. But we do need optimizer. Let me change the order also. Okay, so we pass optimizer. And optimizer is equal to what? Optimizer, right? So optimizer, we know it's stochastic gradient descent. It's got the params in there and the learning rate. Comma. What else do we need to pass? Params. Is that what we call it? Params. Yeah, and params. Okay, good. And then we pass the data, right? So the data, let me just copy that. And this data is going to be the data itself. So same name. T underscore C underscore T. T underscore F underscore T. That's it. That should be it, actually. So then. Cross your fingers. So has anyone tried running it? Let me actually run from the beginning. If there's anything. Have you guys gotten an error? Okay. What is the error?
You gotta run it.
Okay.
Got torch float tensor.
You probably need the square bracket for the params because it highlighted that.
Yeah, okay, so yeah, so the question, your question,
how we can use that.
Yeah, I didn't like it. Yeah.
Use that as a tensor.
What was the error? What did
It
it?
just doesn't like that you don't have the params in the box. The square bracket.
It wants a list? Is that what
Yeah.
it said? Yeah, so that might be it.
It
Okay.
doesn't say that, but it just like freaks out. and says,
Because, yeah,
"That's
you
not
you
the
caught it really well. Let me see what the error was. Yeah, the error is params argument given to the optimizer should be an iterable of tensors
Yeah.
or dictionaries. So it wants a list of tensors here. Okay, all right.
So the square bracket will make it a tensor.
Yeah, that's pretty, yeah, this is by putting the square brackets, that's a list in Python. And so now it's a list of, yeah, so I guess it's because I'm doing the params as a separate thing, and sometimes you can just do it internal. So yeah, all right. So let's run it. And what do you guys think about this? It's doing the, how do you know? How do you what? Ah, it's getting smaller, right? Yeah, it's actually getting pretty small. Consistently, it got to 12.99. That's the loss function. What does that mean? Like intuitively, what does that mean? That the error has been minimized. You guys see that? Huh?
That's something you got wrong and he's trying to figure it out.
Yeah. So now, okay. Now let's just quickly, we'll come back to this. What holds this model, right? So we've got W and B in params, correct? Do we not have params somewhere in here? Where is params? There it is. So y equal model, right? And some value, let's say,
Misspelled PDL.
oh yeah. Model, so really quickly, 0 Celsius should be 32 Fahrenheit, correct? Comma, params, that should split it into 2, right? What do you think? I'm actually pretty happy with the how this turned out. Did it work or no?
Slight error.
It's a slight error, but decent. What's another Celsius? Tell me another Celsius. 100, right? What is that in Fahrenheit? Do you guys know? Or give me one, like
Okay,
who knows like a Fahrenheit to
well,
Celsius?
here's the calculation is Fahrenheit minus 32 times 5 divided by 9.
What's a couple of values? Like
Okay.
give me a Celsius.
So 60, let me try to give you.
Give me one.
100 in Fahrenheit is 37.7.
Okay, so that's pretty close, but 37 in Celsius, right? Should be how much in Fahrenheit?
100.
Should be 100.
37 should be 98.6.
Yeah, pretty good.
Well, so what would you, oh yeah, please.
-40.
-4. So you think because it's like a different, outside the range, right? What's it gonna do? Is that here? So what is it?
Should be -40.
What should be -40?
Both
Negative
are
40.
they converge at negative
Yeah.
40.
I'm confused. What's the Celsius?
They are the
Both,
same.
they're the same.
Oh, okay. So the Celsius is -40. -40. Okay, and you want to see what this is. Okay, got it.
Yeah, good call.
It's close. Close enough.
So what do you say about this model?
Not error, but we're.
But
Reliable.
it's getting close. Give it, well, so, okay, so to conclude, how do you solve this problem? What are the approaches? Yeah, go ahead.
More learning.
More learning time, more epics. What else? Change the learning rate. That's another good one. And what else? Huh? But how do you adjust the weights? More data, probably, what Jason said. Because we only gave it 11 samples. That may not be fair to judge a model that only saw 11 samples. So more data, more epics, and so on. All right. good, so we kind of rushed it a little bit, but we built our first PyTorch model. The beauty of this is that they're all gonna be pretty much the same. We're building computational graphs. We will have this like thing where we have these three statements that do all the magic, and then we will spend a couple of weeks drilling down into this, okay? We'll do like actual calculus exercises where we calculate these gradients and so on. All right, yes, sir.
That's your inference function.
Yeah. Got it. All right, so that concludes the class for today. And I will see you guys next Wednesday. All right.
When will the homework be up?
Yeah, I will try to open it tomorrow,
Thank you.
and I'm gonna give you guys plenty of time.
Thank you.
All right, so yeah, so you built your first model, and this will be the pretty much the same approach going forward.